Hi, in this video I'll provide a very quick introduction to bending moments acting on a cantilever. We're going to look at two common load cases. First of all, those due to uniform loads, for example beam self-weight, and secondly those due to point loads and how they vary as the load moves along the beam. So firstly, what is a cantilever? Well, a cantilever is a beam that is fixed at one end, both positionally and rotationally, and it's unsupported at the other end. So what makes this different, for example, to a simply supported beam? Well, let's demonstrate that by drawing the deflected shape under vertical loading. So if you imagine your support there, and we will draw a deflected beam as best I can. And what you will see there is that the top of the beam has extended in length, so that is in tension. The bottom of the beam has reduced in length, that is compression. There will be a point along what's known as a neutral axis where there's no extension, so that is not in tension or compression. So there's no stress or strain at that point. If you can imagine a simply supported beam under vertical load, that does the opposite, where the top goes in compression and the bottom in tension. For the cantilever, this shape is known as a hog. For the simply supported beam, it's the opposite direction, which is known as a sag. Okay, so let's calculate the bending moment on the cantilever due to a UDL, such as self-weight. So let's draw that out more simply, and we'll have a beam like that, and that beam will have a uniform load on it that I will call an intensity of W, and that the units I use are kilonewtons per metre. So we want to calculate, to start with, at any point along the beam, what the moment is. So if we imagine a distance A from the tip, and I want to calculate what the bending moment is at that point, then we know that the bending moment there is caused by a value equal to force times by distance, where the force is equal to WA, because that's UDL times by the length. The distance is that distance there from the point you're trying to calculate the moment from, which is A over 2. So we therefore know that our bending moment is WA times by A upon 2, which equals WA squared upon 2. And that all makes sense. We know we've got a moment there of 0 because it's a free end. So if you plotted that for different values, what you'll end up with is a bending moment diagram that is curved like that. So let's draw that out for the full beam, and we again will draw the beam like that. The bending moment due to a UDL on a cantilever will look like this, and that value will be equal to M is equal to WL squared over 2, where L is the length of the beam. And if you wanted to calculate the bending moment part way along it, then for example at a distance A from the tip, then the moment there will be equal to WA squared over 2. The bending moment of WL squared upon 2 is a very well used one that you should get used to. Let's do exactly the same again, but this time we'll show a point load, and this is much easier. So this will be part way along the beam, and we'll draw it as a simple diagram with the point load, the value of P. So to calculate the moment, we know that the moment at the tip is 0 because there is no restraint. We know that the moment part way along is also 0 because to the right of that there aren't any forces acting in that zone. And then we come to the point where the point load is. Now a moment is a force times by a distance, so the force by that point load is P, but the distance from that point in question is 0, so we therefore know that we've got a bending moment there of 0. And we're then going to come inboard slightly, and we'll come across, say, a distance A from that point load. And what we know there is that the moment at that point will be equal to the force times by the distance, which is PA, and it's as simple as that. So that would give you a diagram. As your A increased as you got towards the support, you'd have a diagram like that with the maximum value of hog at the support zone. So if we now draw that again a bit neater, but we're going to show the point load at the tip. Again, same, we've got value P. We'll show the overall beam length this time, which is L. And it is as simple as the bending moment at the support is a hog of value PL. Now if you wanted to come any distance A along here, then the moment at that point is equal to PA. The M equals PL is one that you'll get to know off the top of your head. Very easy. Okay, so a quick recap. The bending moment from the UDL was equal to WL squared upon 2. The bending moment from the point load at the tip was equal to PL. Now if you found this video useful, then please click like and subscribe. I'm That Structures Man, and thank you very much for listening.